Just a brief introduction about Dinesh. Dinesh can be described as an all-round IT guru who brings 15 plus years of experience in the IT sector. His vast area of experience holds business analysis, estimation, designing, development, testing, and deployment of IT services. He has done his MS in data mining and human computer interface from University of Illinois, Chicago, and his expertise in artificial intelligence, machine learning, data mining, data analysis, technical architecture, framework design and development, prototyping, architecture design reviews, trainings, and application development. In artificial frameworks, he specializes in TensorFlow, PyTorch, and OpenCV. In languages C, C++, Python, and JavaScript. In data pipeline stack, Apache Airflow, Apache Kafka, and Apache Spark. Deep learning models like ResNet, GAN, RNN, LSTM, and GPT-2. Web technologies, Angular, Vue, and React. In cloud, AWS, and databases, MySQL, Postgres, and MongoDB. This is the specializations and a brief about a brief curriculum vitae of our Dinesh, who is currently working as a CTO of Decrew Technologies, where he was being known to us for a quite longer period of time, and he has been with us giving a guest lectures in our institutions. So we welcome Dinesh, and we hope that participants will get benefited out of it. Dinesh, you can carry on with your work, please.
Thank you, Sridhar sir. Thanks for this awesome intro and heads up. Hi all, I welcome you all for this presentation. Today's topic is going to be explainable AI and model deployment. Before taking you through the explainable AI and model deployment, I'll run a quick recap of what Sridhar sir said. Okay, I come from Dream Technology. I'm the CTO of this company. So it's been founded 4 years back. So this is about me. I did my master's in HCA and data mining in UFI Chicago. I'm one of the founder for Dream Technology. My major focus is AI and full stack. This is my Twitter handle. If you want to shoot up any message or you want to follow me, you can follow me on Twitter. These are some of the apps we have worked on, and in that apps, okay, if you see, actually we do have a few products also. So Identity is one of our AI product. So this is about the company. So ours is an AI first company. We take automation very seriously. It's based in Chennai, and we believe in enlightenment. When I say enlightenment, we take the way we handle the projects, people, AI, and everything is we follow a Zen methodology for that. So with that, these are all the few services as a company we offer. Right from UI UX to academy. So we are very much closely associated with the academy. We train close to thousands of people in AI every year. So that's the services part. With that being said, shall I start the presentation for today?
Yes, please, you can go ahead.
Okay, thank you, sir. So if you got any questions, I'll share my email with Sridhar sir, and you can also send a message, direct message in Twitter. I told you this is my Twitter handle. It's artist, O-R-T-A-S-T. It's artist without an A. Okay. So today's topic is going to be, either interpretable machine learning or explainable AI, explainable deep learning, all falls under similar categories. So I'll better call it as XAI. That's explainable AI and model deployment. We'll take a look at these two things because before even jumping into the topic, I would like to tell you something being following AI. You guys know present day AI is you search for something, you have a model, you can just download the Jupyter notebook or even the Python script or R script, execute it. You'll get to see, if it's a face detection, you can give photos and it'll detect photos. If it's face recognition, you go on the webcam and it will recognize, hey, Vignesh or hey, Dinesh, it'll tell you that. So that's the present state of AI. But so far in the 60 long years, okay, that AI has traveled, okay, the major intriguing factor with respect to AI is, okay, we don't know how it arrived at a conclusion. We don't know why the AI system is behaving like this. We don't know how to debug it. There are lots of don't knows when it comes to AI. We don't know how to deploy it, because right now I have the model, it's working fine, but I don't know how to take it to the user. So those are the two important things that we'll see today. See, this is something that comes after the research. Once you're done with the research, you have the model, okay, right? But you need to take it to the people. You need to deploy it to the outer world for them to use it. So that's when the beauty of explainable AI and the model deployment comes into play. So let's take a deeper dive into it. So what is the present problem with AI? So there are a lot of problems. You may have come across a lot of things in the recent past. Okay. But before that, no, I'll state one single point and I'll move on to the political points. The first point, we don't really know why they make the choices they do. I mean, why AI makes the choices. Okay, that it says, okay, you give a dog's image. Okay, AI says it's a dog. Okay, you give a cat's image, AI says it's dog again. Okay, and you don't know why really it made AI to think the cat is a dog. So that's one of the foremost problem that we are going to solve using explainable AI. And one of the most difficult thing in AI is to debug an AI model and to test an AI model. See, debugging and testing are very intrinsic part of development when it comes to any computer science activities that you're doing, any code that you do or any development that you do. Without debugging and testing, you cannot do that. But that is something AI lacks a lot. There is no debugging, there is no testing that you can do with AI. Okay, so there is a lot of things that needs to be covered when it comes to explainable AI. Let's see how we can, explore that field today. So that's the first part. Second is the bias and fairness. So see, this thing, I'm surely, I know that most of you would have heard about this in the news. Okay, AI is very biased. Okay, when I say a woman works in the hospital and then ask AI to continue it, AI will say she was a nurse and she did her work properly. Okay, and when I say a man at the hospital, AI will say he was a doctor. Okay, he was taking a look at the patients. So again, you see that there is this discrimination. Okay, when you say women, A says nurse. When you say men, A says doctor. So, and then, in lots of facial recognition things, okay, A can identify white people faster than black people. So that is the bias and fairness that we are talking about. And there is, because see, again, let's do this. Okay, A is like a kid. Okay, let's assume, okay, you want to teach a kid. You teach all the wrong activities to the kid and then say, these are all right. What the kid will do, he or she will take the wrong as right ones, right? So similarly, whatever the data that is given to the AI for the AI to get trained, okay, that is what is reflected as the output. If you train most of the AI system for facial detection using white people, AI is going to detect only white people. So you need a balance in the data. So that's the bias and fairness part. Okay, next is privacy and security. So we'll deal more detail into these things, but mainly what we'll focus for today is the explainability part of it and the fairness part of it, and how explainable AI is going to play a major role, okay, in order to solve these two problems. So this is the existing problem. Let's take a training data and you have your nice little algorithm that will take this training data and then gets the model out. Using the model, you can predict the price of the house. Okay, but it will never tell you why the price of the house is this particular value. Why it's so expensive? Is this price the right one? Is there any comparison or reconciliation that it did before telling the price? Or was it an error? How will you know that? Unless and until you don't manually check it up. So that is the biggest problem that we are going to explore today, and we'll see how that can be solved using explainable AI. So that is this thing called responsible AI. Okay, these four things: fairness, explainability, privacy, and security are the four pillars of responsible AI. So if there is an AI, it should be fair enough. There should not be any bias. we should be able to, expect some explainability of the output, whatever the AI throws it to you, and it should take privacy seriously into consideration. Okay, because see, there is a separate field of cyber security for AI that's coming up now. The reason being, there is a lot of data leak that's happening inside an AI model without knowingly or unknowingly. So we know that, okay, AI just stores only the weights, but we can reverse engineer that and get the privacy data that was the AI trained on. That's the privacy part of it. And then security. See, security is privacy and security, like, falls together. Explainability and fairness falls together. Security is also a big factor when it comes to AI. That's the reason VAPT, vulnerability assessment and penetration testing for AI is a new emerging field. Okay, so many AI products are out there, but they are not secure. You don't know the reason. I'll tell you why. In the explainability part, we'll see that there is a nice little paper that came a while back. Okay, you can fool any AI system by adding noise to the input that you're giving. So I'll explain that as we go by. But since most of you come from a similar background, I think most of you can understand when I say, okay, you can fool any AI system by adding little bit noise to the input data. So when I say how we can fool, that's the security part that I'm talking about. Okay, how we can fool an AI. Let's say you have a facial recognition system that will identify the face of the user. Okay, and there is this technology, by changing the pixel values of the input image, I can make the network, the AI model, to predict you as someone else. Okay, so for that, as an experiment, there's a lot of attacks that's been carried around. One of the major famous attacks is to, like, you can have a bindi in your head. Okay, a different colored bindi that will make the AI system recognize you as someone else. That is one aspect of security. I'm just throwing you a few examples here and there. And in the process, if you think this is really intriguing and you want to discuss furthermore on that particular topic, feel free to ask questions right away, or after the session is over, you can ping me. I am available, or also you can message me on Twitter. Okay, that being said, what is a responsible AI? Okay, a responsible AI is the one which will not just say the price of the output, it will also say why the price is that. Okay, if you see, the price of the house is £699, 699,000 pounds. It is located in a good neighborhood, as a garden, and it's fairly new. That's the reason it's priced higher. That's the responsible AI part. Okay. So before jumping in, let's understand what is the model explainability part and how does that fit into the present solution of AI, present deployment of AI, or present architecture of AI. Usually what really one asks is this: they have this input, they have the deployed machine learning model, and then they will have the output. Okay, with that, we are going to add a new layer called explainability layer. And Google Cloud has presently come up with an extension to their existing deep learning offering, which is explainability part. Okay, they do offer it. There is a free trial that you can sign up and play with it. Okay, so you add an explainability layer. What is the explainability function of explainability layer? See, it will try to tell you why this has happened, and it doesn't have to be text always. It can be visual. See, the most of the time it will be visual. We'll get to see some of that. Okay, see, this is understand how ML models makes decisions. Okay, see, you have an algorithm, right? You are trying to run the code, and you see the code is not working. If you don't understand what the code does, will you be able to debug that code? Nope, right? So similarly, we have an AI model. We don't know why it's giving this value. If you don't understand what's happening in layer level, in neuron level, in activation level, okay, those are the three different levels we look into it. Okay, so you'll not be able to understand, or you'll not be able to debug your system. See, without debugging and testing, you cannot get any system perfect, right? That's the explainability part. What is the model explainability? Okay, this is the interesting thing. So model explainability doesn't only depends on the model part of it. It directly depends on the data type that you're dealing with. For example, You can deal with images, you can deal with text, you can deal with tabular data, you can deal with audio, you can deal with any other type of signals. Okay, so depending on the data type, okay, we will have our explainability algorithm such that we can infer more from the data. We can infer more from the output. For example, let's say I'll show you how from these three we infer the values. Okay. First, if you see the images, right? So whatever is shown here is the intensity. Okay, you see that there is this gradient that's running along, right? So this gradient actually defines which is responsible for this particular image to be detected as dog. Okay, what are all the pixels that are responsible for detecting this image as dog? Okay, here if you say, okay, it says the sentiment is 0.9. Okay, in order to score this particular, how could you not love cake? In order to score this text sentiment as 0.9, okay, what are all the different words that's been taken into account? It has taken not and love into account. Okay, and you can also see the intensity of the blue color in that. Not is lighter, love is more. So it says love plays a major role in making this sentiment score. Okay, love plays a major role in making this sentiment score. And there is one important thing that we need to consider when you see this. Okay, see, you can have this, you can put a nice little graph or image like this and take a look at it. After every layer, every neuron, every activation, you can check and see what is the output you are getting out of the neuron, and we can visually see using all these techniques of heat map. Okay, what needs to be done as an explainability part is, okay, what you are looking at, right? The pixels should be such that the words should be such that it's fair. There should not be any bias. For example, let's say instead of telling how could you not love cake, how could Alan, if I say instead of you, if I put Alan, how could Alan not love cake? Okay, and the sentiment score says the word Alan, okay, what? The word Alan, I mean the name Alan is more blue in color. Then the system is biased. Why? You should not take any entities into consideration, whether it's Asian, Caucasian, whether it's Alan, whether it's Dinesh, whether it's Sridhar, whether it's Ramakrishna Mission, whether it's Satyabama, whether it's Vellore Engineering College, whatever it is, right? So there should not be any entities should play a role in terms of the score that you get. And again, it depends upon the problem in hand. Here, what you are trying to score is the sentiment, right? So similarly for tabular data, if you see, for tabular data, we take the feature value, the attribution value, all those into consideration. And this indications, right? The red colors, the blue colors actually tells you, see, these are all outputs you get after the explainability. Once you add the explainability to the network, to the model, you will get to see these outputs. These outputs will help you infer what is responsible, which particular attribute is responsible for my output, which particular pixel is responsible for my output. Okay, recently there was a paper called one pixel attack. Okay, by changing only one pixel in this dog image, I can make the AI model to predict this dog as cat. Okay, what? By changing only one pixel in this dog image, I can make the AI model that this image was predicted as dog to predict that dog as cat. That is the one pixel attack. So basically what is happening is, the dog image pixel. Right? So see, what is actually an AI model? It's nothing but a linear equation, right? A set of linear equations. Okay, and you can literally run through every pixel and see which pixel has more weightage in terms of predicting this particular image as dog. And you change those pixels, okay, and increase the pixel values of the pixels that are necessary to predict a particular thing as dog. Okay, if you change that, obviously the prediction is going to change. So what is really important here is, how a distribution should work, right? Well, there is this theory called, okay, in nature everything is normally distributed. Okay, So should be your data also. So should be your images. So should be your trainings. So should be your testing and validation and everything. Because that's what makes sure just the change in one single pixel should not change the output. Okay, it can add little bit changes. That there can be a delta X change, but it should not change from dog to cat. That's the idea. Okay. So now we are coming to a very important question. Why explainable AI? Okay. See, right now, AI has come to a level where it is getting into the more serious things like healthcare, legislations, okay, really life-saving things, AI are getting deployed. But so far, whatever you have seen, the AI is like a recommendation engine, email spam filtering, some text processing, some images that will say this is a dog. Okay, that is all fine. But the real challenge comes when it deals with life decisions. And I'll tell you why that is a problem, right? See, let's take an X-ray. A radiologist, can take a look at the X-ray or a scan and then say, okay, this person has this particular issue. Okay, why? If you ask the radiologist, why do you think he has this particular issue? He can, pinpoint at few places in the images and say, okay, hey, this is like this is like this. It should not be like this and everything, right? But that substantiation you cannot get from AI. It's our responsibility. If we want AI to be taken into the medical field, AI to be taken into the legislation field, where if you ask a question to the AI, why did you predict the person as more likely to develop heart failure? AI should be answer that question to you. Okay, right now, there is like a lot of things that going along the lines, but whatever the system that is deployed right now doesn't have that much explainability capability to tell you, this is the reason I said this person has heart failure. Okay, so that's the very important thing that we are facing today. See, these two things, right? The explainable AI and model deployment are the major activities that we are seeing in the recent past. Okay. So how do you verify a system that until okay it's a false proof, failure proof system? Okay, and that too, it should be a false proof, failure proof system when it comes to finance, legislations, and healthcare, right? So that's where right now AI is trying to get into. Without those verifications and explanations, you cannot arrive at that. Next is the improvement to the system. Okay, see, let's say you have a system or model that gives you accuracy, let's say 85%, and you want to increase that accuracy to 98, 99. What should you do? See, there is a lot of things that's been spoken with respect to changing the data, adding dropouts, having different types of models, like doing an ensemble technique, changing dense layer, ResNet layer. We have dealt with a lot of things that can be done with respect to hyperparameter tuning. That is all there, I agree. But we need more explanations in terms of, let's say, will you be able to fix a code if you don't get a stack trace? Will you be able to debug a code if you don't get a stack trace? No, right? Similarly, we should have a way to tell, okay, we should have a way to track back, okay, the output, and then inspect every layer in the AI, inspect every neuron, every activations, every dense net, every ResNet, every dropout that you deploy, okay, every hyperparameter tuning has to be, we should be able to inspect that and see how a change in one can affect the other. And based on that, we should be able to change our, tweak our input data, tweak our activations, see, this will help you achieve better accuracy, achieve greater accuracy to be more precise. Okay. So that's the one. And then when we speak about learning from the system, that we'll see something later on. So coming to a very important question, who needs all these explanations? So we have domain experts, we have users who are using those models, we have regulatory entities, because right now, if there is even, let's take Europe, right? They have this GDPR and we need to meet GDPR compliance. Can anyone give certification that an AI system is GDPR compliant? No, there is a lot of problems with that, because GDPR expects a few functions. When I say pure function, if I give 1 + 1, it should always return 2. And that is something you cannot expect from an AI. It can return 3 also. Depends upon how you are, what adversarial effect you are used, adversarial attacks you are used to, a change in the pixel value can change the output. So, and data scientists, developers, see, and I mentioned in every place who needs it and why do they need it. Okay. So very important, the regulatory entities, they need it to certify the model compliance. See, you need to have an audit trail also. See, when it comes to software development, we have come a very long way. We have so many methodologies. We will see that, comparing AI with software development during our model deployment. Okay, during our model deployment, we'll dive deep into it. But right now, to start with, let's see more of explainability part. Okay, so for example, for data scientists, developers, okay, how they can improve the product efficiency. It's very important for them to improve the product efficiency. So they need to inspect every layer and see. Okay, for domain experts, how they can trust the model. Okay, can a radiologist who is a domain expert in reading CT scans, okay, he has to trust the model more than him. So in order to trust the model, he will have a checklist, and you should be able to question the AI system with the basic checklist and then get it covered so that you can trust, okay, the output given by AI is right. We can rely on that. Okay, that's the overall who needs the explanation part. So now we are trying to come into the actual part of learning more about the explainability. Okay, so explainable AI is, in short form, it's called XAI. There is this taxonomy. There are different ways we can think about an explainable AI. One, can it explain a particular model? Okay, that's a different category. So in that we have two specific models. One is model agnostic, model specific. Okay, when it comes to model agnostic, that means one single explainable AI model can handle, can just, it's like a plug and play. It can get into any models that you have and then, infer details, intrinsic details from the layers. That's the model agnostic part. Next is model specific part. Okay, some are developed specific for the model. Okay, so that's the model specific part. Does it explain a particular sample or the entire model? Okay, that again tends to know whether we are going to we are trying to tackle. See, again, what explainability model you are going to use and how we are going to do it. It totally depends upon the data you're dealing with, the data type. That's something that I spoke a little bit a while back, right? Here, the data type that you're dealing with is very, very important. And also, this explainability AI is very much useful not only in understanding why the decision is made, in also understanding and debugging the code of AI. So in also debugging your model, it is very much useful in debugging your model. If you think, okay, your model is stuck in local minima, okay, then this debugging will obviously help you to get it out of the local minima and try to achieve a global minima. Okay, so there is also when does it occur? So where you are trying to put the explainability part, in the pre-model part, whether inside the model or post-model, totally when the forward pass has completely happened and it has predicted something, and after the prediction you are trying to do your assessment. That is one. And inside the model you can do your assessment. That is two. And even before getting into the model, you can do a few assessments in the input itself, right? That is the pre-model part. Okay. So finally, does it work separately from the model or does it visualize the model? So right from the start, okay, this question about, okay, can we interpret machine learning algorithms? Okay, it's always dealt in very visualized fashion so that it's easier to catch it that way. Okay, so this is the today's scenario of explainable AI. We have training data, we have machine learning process, we have the learned functions, and then decision is made. But here, if you see, we have a lot of questions. Why did you do that? Why not something else? When did you succeed? When you failed? When can I trust you? How can I correct an error? So now what we are doing is we are adding these two things, very important things, to the AI pipeline, the explainable model and the interface. Okay, using this, we try to answer all these questions. Again, it's not an easy task like this diagram. We can just change this and it'll work. Okay, there is a lot of debugging that needs to go for you to achieve this in first place. Okay, so with that being said, we'll see few explainability tools that are used in the market and why they are are really successful. I'll not even say tools; they are also a model and algorithm. Okay, we'll just start with retain, reverse time attention model. So you should have heard about attention mechanism, right? In deep learning. Okay, see, attention mechanism actually works in the forward pass of the network to let you know, okay, where you should pay attention so that you can take a particular decision. For example, especially in natural language processing, okay, you'll have a sentence. Okay, I met Suresh. Suresh is a nice guy. He tends to be a little tense in the recent days. Okay, he's okay now, I guess. So that's the sentence. Okay, so see, initial first two sentences I actually referred Suresh as Suresh. So when you do entity classification, you will be able to identify that Suresh is who I am referring to. But when it comes to like 3 or 4 sentences after, I refer him as he. Okay, only if the if there is a way for the network to capture that the particular word of Suresh is what this he refers to through an attention mechanism, there is no way that the sentiment of the whole sentence and then what is the present sentiment of Suresh? Suresh is doing good now. That's the present sentiment. Okay, but since we have not included Suresh in every place, okay, there is a chance that after 3 or 4 lines, the Suresh is actually left out. And in between, we would have talked about, Suresh met with his friend Ganesh. Okay, and the A would, think, okay, Ganesh is a little bit tense. Ganesh is all right now. So that, in order to, overcome this, there is this particular thing that gets deployed in an RNN called attention mechanism. We are going to use the same attention mechanism to, but it's a little bit different in terms of it's a reverse time attention model. Okay, because we are going to apply a little bit a reverse technology to get it done. So for explainability, so recurrent neural networks makes use of attention mechanism to improve interpretability. Let's see how it does it. Okay, so usually this is what happens, right? There will be some predictions. Okay, and there will be here in terms of retain. So this model is called retain. Okay, so in retain, what we do is like we do a couple of runs. One is called the beta RNN, another one is the alpha RNN. Okay, from that we take the embeddings, and then we'll be able to using these 2 runs, we'll be able to come up with the explanation why this thing has happened. We'll get into the details. Okay. Okay. For this, I've also given you the reference paper. Okay. For this, let's take a scenario. Given a patient, okay, see, hospital visits records, okay, which also contains the events of the visit. They would predict the risk of heart failure. Okay, so based on the patient visit, okay, what we are trying to do is we are trying to predict the risk of heart failure. Usually what happens is that when you run this into a recurrent network, okay, recurrent network will usually say, hey, this patient has high risk of heart prediction, medium risk of heart failure, or low risk of heart failure. Okay, but the model will not tell you why this person has high risk of heart failure. Okay, maybe we can run a few visualizations and try to understand why the output is like that. Okay, and that is what we are trying to solve here by taking the input, split it into 2 recurrent neural networks. Okay, and then having an attention mechanism for the network to focus on few things. Okay, once the model is trained and then you predict, let's say, okay, it will take alpha and the beta parameters. That's the most important thing. Now we have two parts here. One is the alpha and the beta, the alpha and the beta. It will take the alpha and the beta parameters and see which has influenced, okay, see which has influenced the choice of predicting it as risk of heart failure. So thereby you take no parameters into consideration, and then you tell, okay, which hospital, see, not only that, see, if you ask me, okay, you are talking about alpha and beta parameters. What are those parameters? Which hospital visit? Which events? Okay, within a visit. Okay, so within which visit? So all these things, all these parameters, see, basically I'll tell you what the parameters looks like. You see this, right? The distance, the starting hour, max temperature. Similarly, here, this is what we are trying to explain here. The distance plays a major part in terms of, recommending this particular system. The starting hour plays a major part, whereas the temperature doesn't play a major part. See, this is important. The reason I switched back is, see, similarly, okay, by just, going through the parameters, okay, alpha and beta, see, what really happens is there is a small change. Here, when you use this system, what you'll get is, okay, let's assume 0 is low, 1 is high. Okay, let's assume it's a binary classification. Okay, 0 is low, 1 is high. What you get out of output as this system is, it will either say 0, 1, that's all. Okay, whereas in this system, what you get is, it will say 0. At the same time, it will also say which hospital visit, okay, within a visit, okay, which are all the visits is the influences. Okay, it will also give you other parameters as output. That is mainly taken from this events of this beta and alpha RNNs. Okay, it'll take only few from this, and then show it as part of the output. Not just low, also a couple of attributes from here, couple of attributes from here. So what you get as the final output is some 4 outputs. One, it says low. Why it is low? Because all these parameters are like this. Okay, so that's the retained part. Okay, next is, this is again one of the most famous in terms of interpretable model agnostic explanation. Okay, LIME, we call it as LIME, local interpretable model agnostic explanation. Okay, so what is model agnostic? Okay, there are two things that we already spoke about, right? One is this one, model agnostic. Another one is model specific. Okay, so what is model agnostic? It can be applied to any model, okay, in order to produce explanations for its predictions. Okay, that is model agnostic. Okay, whereas model specific or post hoc model, it's called post. Okay, it provides an explanation of the decision after it has been made. Okay, there are two things that you need to understand when it comes to LIME. Okay, LIME is model agnostic and it's post hoc. When I say post hoc, LIME will give you no explanations of after the decision is made. Okay, so for example, this is the model, this is the data and the predictions. Okay, we pick up few states and then we get the explanations. So, okay, human makes the decision based on the explanations. Okay, so two things. One is model agnostic, another one is post hoc. Okay, provides an explanation of a decision after it has been made. Okay, so how does it work? The approach. See, usually the approach is first, okay, whatever it is, the AI model, it's a black box model, right? AI model is usually it's considered as a black box model because you give the input and you expect the output. Okay, you doesn't really know what's happening inside, and that is what we are trying to know. Unravel it today through the explainability model. Okay, so use a black box model, okay, to produce a probability distribution over the classes. Okay, you have a few inputs. Okay, give it to the AI and get the output. Okay, and note down all your outputs so that you have a nice probability distribution model. Okay, then take the input. Okay, perturb the input. That is basically disturb the inputs, change it. Okay, it can be as simple as hiding pixels by coloring them. Okay, if it's an image, it can be as simple as hiding a pixel value or increasing the brightness of the value, decreasing contrast of a particular pixel value. Okay, that's an example for perturbing. Okay, now after you perturb your inputs, run and see the predictions. Okay, take a note of all the perturbations you did. Okay, and take a, the change in distributions because of the perturbations. Okay, construct a nice little decision tree. Okay, with the perturbations and the probability. Okay, so and extract the key features from the decision tree. See, what does the decision tree will help you? Decision tree, in order to understand the decision tree, see, based upon decision, you traverse a particular path. See, it can be as simple as a binary search tree. Okay, so what does a binary search tree do? If I have a tree and then you have a value, you just need to traverse down the tree to arrive whether the value is present or not. Okay, you just traverse down the tree and then based upon the what does a binary tree do? It splits up into equal halves and it sorts it. So you, for example, if the number is lesser than the value you are finding for, you'll take the left hand side of the tree, and if it's more, you'll take the right hand side of the tree. Similarly, a decision tree is a machine learning algorithm that takes that traverses a tree based upon the conditions that it evaluates. Okay, so with the perturbations and the probability, we have constructed a nice little decision tree. Okay, that decision tree will help us to extract the features, the perturbations that it changed. Okay, which can explain the change. Okay, so what is the output? Output is the pixel values. The pixel values, the weights of the pixel values that made a major role in terms of getting the decision, getting the probability change. Okay, that is what is the output you will get out of line. Okay, so again, that is this. Whatever I said is explained here. Start with a normal image, use a black box model, then perturb the input in some way. For example, it can be hiding pixels, coloring them. Okay, then use interpretable models like decision trees. Okay, from the decision tree, what do you get? You can get the particular features. Okay, the model is locally weighted, so the output will be the greatest weights as our explanation. So the output features that you get out of the decision tree are the actual features which plays a major role, okay, in terms of your classification. Okay, so what we can do now is like we can make sure these features, right, are the very important to the model, and we can also make sure the algorithm is not biased to these features by adding more values to it. We can add more inputs such that the bias for that particular feature goes off. The bias for a particular pixel will also go off. So when you add things like that, you can surely say my system is fault tolerant. So you cannot have anything like an 1 pixel attack in my system. Okay. So next is another important one. See, there are 3 things that we will see. One is the retain, another one is lime, and the last one is layer-based relevance propagation. See, layer-based relevance propagation uses the idea of relevance redistribution and conservation. Okay, so again, start with the input and its probability of the classification. So it's see, for everything you need to have this distribution first, right? Without having the distribution, you cannot literally know how the data is and what is the relationship between the input and the output and things like that. Okay, so we always start with this probability of the classification, basically a distribution. Okay, then you work backwards. Okay, to see again, think of this as your back propagation. So you know what a back propagation algorithm does is, right? So the only part that do here is like differentiate to go backwards. We do redistributions. Okay, but how does a back propagation work? We need to adjust the weights in the previous layer. So we need to back propagate. Okay, and then try to change the value of the weights based upon the loss, right? So it's a similar mechanism that's employed here, but it's especially thrown to the explainability part. For example, see again, a picture is worth more than 10,000 words, I say. So let's say this is the input we are trying to give into the system, and you can easily know once you have the model or you download the model. So right now, A is in a state; it has reached a state where no other programming developments has reached. That is, you can simply search in the internet and get the code and then run it and work. But the major thing that you cannot do as you do in the code is like the debugging part. Okay, what do you do usually when you code? Like you copy paste a bunch of code, you debug it, you change, you adapt it to you. and you deploy it. Okay, but the major problem now in EA is not the the model. The model is up there. Every model that comes out, there is like thousands of paper published every day in AICTE. Okay, and the state of the art is there for you to download and experiment, for you to download as a notebook and experiment, for you to download as a data set and experiment. Okay, but the major challenge is, okay, after downloading, you can run it. Yes, you can run it. You can see the output. Wow, it's working fine. But how do you adapt to your system? How do you debug the system? How do you know whether it's performing right for your data? And remember, there is no one solution when it comes to AI. Okay, every model is unique to the data that it's trained on. Every model is unique to the distribution of the data and the output is trained on. Okay, so even if you download any models, because today all the paper is out, everything is open source, you can download whatever Google is using, whatever Apple is using, whatever Amazon is using. You can achieve that much accuracy. Okay, that model is open source and you can download and use it. But the major problem arises when you want to adapt it to yours. When you want to debug the model, that's where this explainability, comes into play. And the next major part is the next major problem is the deployment part. That is our second half. We'll see that. Okay. So, for example, let's take this image. It takes all the pixels in the image. Easily does this, dot product of the weights and the vectors, and then finally does the activation. Finally gives the output. Says it's a cat. Okay, but you really don't know what played a role. See, this is where relevance propagation comes into. So you take this, you propagate it. Okay, you see all this like says, this darkness actually says, okay, which particular neuron played a major role in terms of, taking this as a cat to the output layer. Okay, and we can make sure, okay, this particular, we can backtrack and see which pixel actually, carries that weight. So that's the layer-wise relevance propagation thing. Okay, so this is again, whatever we saw so far is just an, an overview of, explainability. Okay, and after completing the model deployment, I'll tell you how we can, actually do this explainability in. There are like few online tools that are available. Okay, you can try that. It all started with, TensorFlow Playground. You can take a look at TensorFlow Playground. I'll also, finally, I have a 10-minute session. I'll walk you through how you can, learn about explainability in TensorFlow Playground and also in, What If tool. Okay. So there is also one more tool that Google and OpenAI together have came up with. Okay. We'll see those three tools at the last. Okay, so this is again a nice overview of what an explainable AI is and what is the taxonomy and three important algorithms that's usually used in explainable AI. One is the retain, lime, and LRP. Okay, with that being said, I'll slowly jump into the model deployment part. See, the major problem the data scientists are facing now is this. Okay, even the explainability, some of the data scientists were able to get it right. But when it comes to model deployment, when you take software engineering per se, or software development per se, okay, it has come a long way. They have like a lot of things in terms of telling, okay, keeping the system up 99.99999%, keeping the system updated every minute, okay, keeping the system available always. Keeping the system updated, keeping the system available, making sure the deployed system is bug-free. Okay, because they have test strategies. They have lots and lots of tests. I'll go through a test pyramid that is very important when it comes to model deployment. Okay, to make sure the model or the software that gets deployed is bug-free. And they have several pipelines, continuous deployment and integration procedures. Okay, to make sure continuously people are getting updates, because in the present world things are changing every day, and you need to push your code every day to make the latest available to the people who are trying to use our product. Okay, this particular thing falls under the category of ML ops. Okay. So you would have heard about DevOps, GitOps, and this is MLOps. Okay. So let's see again the topic for this. I'll name it as like CD for DL. Okay, continuous deployment for deep learning. Okay, let's first look at a simple architecture. See, this is the assumption. I'll tell you what are all the pain points. What happens when you have only data scientists? What happens only when you have software developers, and how the problem that we are facing today and how we can solve it and everything. Okay. See, as I told you before, software engineering and development has come a long way. Okay, they have like lots and lots of test strategies, procedures for deployment and integration, and making sure the system is available always. Okay, and that is not the case with the model. The model is treated as still in the research phase. After the research phase, you convert that into a model and hand it over to a team that doesn't know what to do with the model. Okay, that's the present day scenario. Okay, so this is a simple architecture. You have the training code, you have the label data, you build your model, and finally you have the model. You can, the model gets to saved in a serialized format, can be PE, MML, or 1H format or anything. Okay, once it gets saved as a model, you have the web app code, you deploy them together, and this web app is available as a REST API, and you push it to the production. From the production, a user coming in the front end can, using the REST API, can get the details. For example, it can be as simple as classifying a dog or a cat, or medical data production, or any recommendation engine. Okay, so this is a simple architecture. This is what we are trying to achieve. Okay, but let's see, as get deep inside everything, you'll face a lot of problems. Okay, we'll see that. Okay, now the first problem. Okay, see, like the software development, YAML deployment will not happen like that. It happens in silos. Okay, so it happens in silos. When I say it happens in silos, okay, the problem is, even if you have the team integrated together, they are sitting together, whatever it is. Okay, we have data engineers, we have data scientists, we have ML engineers, we have ML ops, we have developers. Okay, we have all these pieces, right? See, mostly the DevOps people and the developers and the testers work together. They understand the language because it's a long-standing problem that's been solved. But now the problem is like how to deal with the data scientist part, how to deal with the data engineers part. Okay, see, the data scientists majorly focus on this part. He makes sure, okay, the training code is there, the model is getting built, and it's serialized and it's available as a model for you to consume. Okay, the data engineer, whereas, okay, he spends a lot of time in terms of, setting up, the sources, where to get the data from, and how to label them. Okay, how to segregate the data, as this should go as the training, this should go as the testing and everything, this should go as the validation and everything. Okay, so this is what happens when you work in silos. Okay, see, the work literally happens like this. Now, how we can break the silos and then make sure the deployment is totally possible is what we'll see now. Okay, okay, and this is a simple pipeline. Okay, you have data, you split the data. Okay, for anything that comes in, you use a Python file. That's the splitter.py. You split the data into training data, validation data, and you keep the test data as such. Our test data will be real data inference that you do. Okay, then you give that training data and validation data into a decision tree. That is, the model gets a decision tree, and you have something called evaluation also. So this is where the explanation and all those things comes into play. The decision tree, PY, and evaluation plays a part of explanation AI. After the model gets trained, you save that as PKL file, and then the metrics. See, before running through this pipeline, first let's understand, and I guess like most of you being in the present day world should know the development happens. How does a web app or mobile app, or for that, any software per se is getting deployed. Okay, they will have a data store, a backend database, or even the data store, a backend script, basically called the server-side scripting or the application layer. Then comes the front end, which talks with the backend using a REST API through a HTTP protocol, or it can even be a socket, okay, using web sockets. And the user will query the front end, and the front end talks with the back end from the REST API and gets it. See, this is what you get to see. But in the back end, when it comes to deployment, there is a lot of monitoring, there is a lot of logging, there is a lot of testing, there is a lot of continuous integration, there is a lot of continuous deployment that's going on. Okay. What we are trying to see today is like how we can bring those knowledge here into the DL pipeline so that we will also get to see the monitoring. So you need to monitor your models, change in the model performance, right? Only then you'll know, okay, this particular deployment has made this model to behave like this. Okay, that's where explainability will help you. Okay, see, this is again a simple pipeline. So this is the test. And I see most of you are coming from an academic background. And the major problem with the academy is academy doesn't take test into account at all. Academy works on research. Academy works on output. Okay, academy doesn't teach test. I think that is something that we should incorporate very seriously moving forward, because software industry or the whole of computer science industry doesn't work without test. A test is the most important part in the whole development life cycle, more than the development. Okay, which is not taught in academy. I don't see any specific things that teachers test very seriously, because we always focus on the development part of it, getting running the algorithm, getting the output, not to making the output generic, not to have all the tests that needs to run. See, the reason to put this is the AI industry is just now waking up for it to run through all these tests. There is no testing strategy that is as good as a software development testing strategy. Okay, so what we should do now is to take all this testing knowledge that we got through our software developments and get them inside the AI test. Okay, the most important test of all the tests that we do is the unit testing. Okay, unit testing in AI is a separate subject altogether that needs to be brought inside the academic curriculum. Thereby, we can produce literally good products as well as good AI engineers out of the academia. Okay, so so that's the reason the pyramid starts with the unit test. Without unit test, there's no test that you can do. Okay, next is like you do all these are performance, bias and fairness. All this tests should be considered when it comes to model deployment. See, usually when you do a software deployment, right, we do consider a few tests. What are the tests? We'll put it in a pipeline and say automation script that will run the unit test. Yes, automation script that will run the integration test. Automation script that will run the end-to-end test. And then finally, when everything gets passed, we'll deploy the code. Okay, see, again, this is what we're talking about. The bottommost unit test, and then integration test, end-to-end test. Okay, these are the three important tests that we do in a software specific deployment. And there's one more test that we do in a software specific deployment. That is part of the end-to-end test. We'll call that as security testing. Okay, checking for security holes. Okay, so when it comes to AI or DL or ML, okay, we have few other things that needs to be tested. Okay, the data validation, the data pipeline, the ML. See, data pipeline and ML pipeline are a little bit different. See, when you say data pipeline, how your data gets transformed, the ETL pipeline. Okay, when it gets to ML pipeline, from the ETL, whatever you get out of it, you should do an EDA, exploratory data analysis, and it should pass through few algorithms. You can also have multiple algorithms running at the same time. That is the ensemble ML pipelines. Okay, and then you take the model performance, model bias. See, this model bias and fairness. In order to do this, you need to have the explainability model integrated in your pipeline here in ML. Okay, then you do the regular test that you do with integrations, end-to-end exploratory test. This is the pyramid that you should be, looking into when it comes to model deployment. Okay, and this is the whole end-to-end architecture. Okay, we have three important things. One is the data, another one is the model, another one is the code. Okay, when it comes to the data, people always think Data is the data that you take and then you put the training data, validation data, test data. That is the data. No. There is this data of metrics that you collect. That is very important. Okay. There is training data, there is test data, there is validation data, there is metrics that is very, 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 very important. There is monitoring data that you get for every run that the model encounters, so that you can do an audit check, so that you can do an audit, you will have the audit trail so that you can audit it and then say, hey, okay, this is when it failed, and can we take a look at the input that came in? And can we take a look at the explainability output during that input? Okay, see, explainability, I keep telling the explainability part even in the model deployment, because the explainability has helped us debug the model, test the model properly, and then deploy it. Okay, so it starts with model building, model evaluation, and instrumentation. You can see what are all the things that place in terms of model evaluation. See, as usual, right? From the academia, you would have done these two things: the model building part. You'll have the training code, you'll have the test data to validate. That's the model evaluation part. That's it, we are done. No, we need to prioritize the model. Productionize. Productionize is it's a simple word, but it includes a lot of things like all this. It should solve all this test before even getting to this part. Okay, the test part. That's the productionizing part. That's the ETL pipeline part. That's the ML pipeline part. Okay, those are all will make sure it's productionized. Okay, next is the testing, deployment. Okay, what we are talking about now is this part, this deployment part. The next one single image is what is very important. That is how we deploy some of our models. I'll also show you a few demos of our product, in-house product, and I'll also walk you through a couple of explainable interface. Okay, so monitoring and observability. See, again, this is something that should be taken very seriously. If you take any software development, there's a lot of monitoring tools. They have the likes of ELK, the likes of Grafana, Kibana. They have Graylog, Prometheus, Wazoo. They have NetData. Lots and lots of things just to monitor the health and the output, the logs. So we should also take logging seriously into consideration when you build an ML model. Okay. So, and finally, I'll show you how you can deploy a model in production. Okay. So this is the final diagram. Usually this is the case. As I told you, there will be three things in a regular software development. One is the app. Another one is the backend REST API. And the final one is the database. Okay, from the DB, the REST API will get the data and then gives it to the front end. Front end can be React, Angular, Vue, your normal HTML, CSS, or even your any desktop-based things also, and even a Python. Okay, so what happens is that but with ML there comes this part. Okay, we'll see this part. Okay, with ML, there comes this part. Okay, how does ML start? It starts with business understanding. Okay, and then you need to understand the data, prepare the data, and then you get the model, right? So after modeling, okay, that's where these two things comes in. Okay, after modeling, that's where these two things comes in. Okay, so you have the model ready. Okay, what should I do? What you should be doing is evaluate the model. Okay, evaluation of the model should meet the business understanding, because you should evaluate it against the business requirement. Okay, once you evaluate, this is a vicious cycle that goes back and forth, back and forth, back and forth, back and forth. Okay, once you think your model is ready and evaluated, okay, serialize the model. These two black boxes are that. This is evaluation, this is serialization. Once you serialize the model, put it inside a data store. It can be S3. That's what we use. Okay, put it inside a data store. Okay, from the data store, the model gets consumed. Okay, so usually what we do is like when it comes to DevOps, right? So once the model is done, and then push it to the container registry. Okay, Docker container registry, and the change will be picked up automatically, and it goes through all the test cases that you saw here. Okay, once it passes all the tests, okay, the model container will be available for the Flask. The existing container will be replaced with the new container with the new model. Okay, Flask, as usual, what it does is like, okay, it does hit the model with the same query, and it gets back the latest improvement for the query, and then this is given as the REST API. The major problem we see in terms of organization, in terms of researchers and academia, is that okay, people who have this web development background are separate, and people who have this deep learning are separate. Okay, deep learning knowledge or model-based knowledge is separate. So it's the working in the silos as this major problem. Okay, the way we can come up with a product is because okay, we are very much proficient in two things. One is the full stack for the web, and also we call it as like full stack for the deep learning. Okay, so it goes through this vicious cycle, and your model is available. Convert that model into a serializable format, store it in a have it in a store. Okay, if you are ready, push it, change the make the new container to be picked by the Flask. Okay, the Flask gets to interact with it directly, and then the same REST API. You don't have to change anything with respect to the REST API. It's available for the front end. Okay, and whatever it is, right? The data. If you want the model to be trained on the new data that's available, from the DB you take the data. If you want once the model is ready, if you want to like change the instance of the model for the store, you can directly talk to the MySQL DB, and then for most of ours we use MySQL. That's the reason we have, and most of ours we use S3, and we use Docker and mostly Angular and also React. Yeah. So these are the frameworks and tools we use. So with that being said, this is the gist of the whole model deployment. Okay, and I would not even say we spoke just about the model deployment. We spoke about the continuous deployment for deep learning. Okay, how you should take a continuous deployment for deep learning. Okay, so again, see, of late we have turned up very much to PyTorch. In the early days, yes, we were using Keras, TensorFlow, Scikit-learn. Still we use, for some we use TensorFlow, but majorly we use PyTorch. Okay, it makes things simpler, and it makes our software engineers also pick up this deep learning easily, because they don't have to think in a computational graphical flow. They just need to think in a programming graphical flow. Okay. So, and when it comes to, we have this product identity. And we have few AI principles that we usually follow. One is the fairness, the transparency, the accountability, non-discrimination, notice and consent, lawful surveillance. Okay, see, all these things are possible because of the explainability part. If not for the explainability part, we cannot do all this. The fairness, you cannot estimate the fairness of a model unless and until you can, give an explanation of the output. Okay. So I'll quickly, run you through a couple of demos of our product, and I'll also walk you through two tools that is used for you understanding the explainability, and after that I'll be ready to take questions. Okay, so this is visual intelligent robot that we built. It's in our lab here in Chennai. It's completely 3D printed from scratch and built by us. Okay, and I'll quickly show you what this is. No, just skipped. I don't know whether you guys hear this sound. There is a music behind it. And this robot was like completely built from scratch every part that you see there is an open source 3D printable object. We printed that, we joined it. It's got real eyes. It's got a camera using which you can, So I'll quickly run through this so that we can spend time on our model.
Dinesh, there is no
Yes.
sound. There is no sound.
Oh, there is no sound.
Yeah.
1 second.
1 second, you have to share it in such a way that the sharing part should be having a sound in your screen.
No, sorry. Can you repeat that?
See, in share screen.
Okay.
In share screen, there will be a sound sharing. At the bottom, there will be one check.
Hi. Okay.
Click on that.
Okay.
Share
screen.
Share desktop.
Bottom, huh?
Let's check it up.
Stop share is there. Share screen is there.
I
have to stop and share it again.
Yeah, please.
Okay.
In share screen, you have to take up the share.
Advanced sharing option is there.
Yeah, in that sound is share desktop sound will be there. Check it up. Whether you are.
No, I'm checking. No, it's not there.
Okay then. That's all. 1 second, we will check it up here. Share computer sound will be there. No? Share screen will be there. In that share.
It says how many participants, who can share, who can start sharing. That is what is there.
No. In share screen, once you click the share screen.
Oh, okay. Once I click the share screen, yes.
At the bottom, there is
share computer sound.
Oh,
yeah,
yes,
okay.
Yes. Do that.
Yeah, got it. I'll share the whole desktop now. 1 second. I don't know whether you guys see it. Let me know.
Sound. You give the sound.
Hello?
Yeah. We are able to hear the sound. We are able to hear the sound, Dinesh.
Okay. Quickly skip through it. So that is one. And now we'll look into our product. Okay, one of our product, it's Identity. It's a AA product. It does a few things. I'll quickly, jump through that.
Hi and welcome to Identity.
So this is a small video of our AI product. It's got no real-time recognition, attendance registration, social distancing alert. It's got no document extraction and retail analytics, a few things. So with that being said, let me move on. Okay, so with that we come to the last part of the presentation. Do you guys hear me? Hello?
We are able to hear you.
Okay. So as the last, before jumping into the last part of the, do you guys like any questions?
Yeah,
I'll walk you through a couple of tools. Okay, before that I'll take a few questions. Yeah.
Applications of explainable AI, please.
Okay.
From Dr. Prashanti Boyapati.
Okay. Applications of explainable AI. See, again, explainable AI will let you, make your AI acceptable in first place. Okay, the major challenge now, okay, by no means you can tell why my AI system is giving this output. Okay, explainable AI is applicable in everywhere AI is applicable. Okay, but there is this urgent requirement, okay, that in terms of healthcare, finance, okay, and legislation, where it's very, very important that you cannot, in healthcare, in finance, in legislations, you cannot take risk of a false output, right? Even let's say Amazon, you go to Amazon, you have your recommendations, right? Okay, if you don't have an explanation there, it's not a problem. Okay, we think, okay, based upon the purchase rate, we can say my AI is performing better. It has increased my churn rate, it has increased my revenue, it has increased my top line and everything. Okay, but when it comes to very serious things like healthcare, legislations, and what did I say? Healthcare and legislation, finance. Okay, one source of truth is important, and it's either 0 or 1. It's binary. It should be binary. So we need explanations. Okay, those 3 major areas you should try targeting, and these 3 major areas are taking explainable AI to other areas also. So wherever you see AI, we need explainable AI there. So it's everywhere only. It's not with respect to one. Next. Does it answer your question?
There is another question.
Yeah, please.
Which software model or model used to develop from face recognition system? You can click on the chat where the questions have been shown.
Okay. I'm trying to get to that. But this is, okay. I need to switch to Zoom first.
Oh, this is Apple somewhere else. It's
yeah.
No problem. Then I will let you know.
No. I'm switching it. Where's the chat part?
Zoom.
What?
Just in the bottom, there is an icon, Zoom's icon, no?
Zoom icon is there. This one here.
Yeah, click that. That is the part in which you are.
Remote control, annotate. I don't see chat. I click here. Chat is here. Okay, fine. Great. Okay. Thank you. So, wait.
That's all right.
Okay.
So which question is which software or model used to develop a face recognition system?
Okay. So we used PyTorch, and we have an ensemble technique that uses retina face, DLib, MTCNN, HAR cascade. Depends upon the requirement of the client. We take the particular model. Depends upon the system that's in place. For example, they want a real-time system in place. Yes, we use retina face. If they want something that's only a CPU based, we use DLib for that. Okay, and if it's in between, they are okay with small performance updates, and only for post processing we use MTCNN. So those are the models, and retina face, MTCNN are the models, and we have implemented the whole thing using PyTorch. The layer is front end is Angular, back end is Flask. Anything else? So you can ask me anything, related to that, how we have deployed, whether it's on-prem, whether it's cloud deployed, or how do you have your monitoring there? How do you continuously update it? How does the model continuously gets updated and everything? Yeah. Any other question? Okay, so until maybe you people can think of the questions, I will switch to the two tools that I was talking about. Very, very interesting tools. Okay, I'll close these two. Okay, the first one is this, playground.tensorflow.org. I know all you should have started dealing with the AI and the deep learning with the regression problem, right? And all of you would have heard about what happens when your data are linearly separable, what happens to the classification, what happens when it's non-linear and everything. And in the due course, you would have also learned about few things like regularization and overfitting, underfitting, right? So all those things you would have heard. Okay. So this particular, it's actually gives you a visual understanding. Okay, visual understanding of how you can, see, do you have any theories like, okay, for this problem, I will have 2 hidden layers. For this problem, I will have 10 hidden layers. For this problem, I will have 15 hidden layers. Can you come up with something like that? No, right? Unless and until, okay, you know the data, or you have some ways to debug every layer of the data, or some ways to know how the data is separable. You cannot come up with something like that. Okay, so that's the whole part of this. You can add more hidden layers. You can add more neurons. You can add some regularization parameters, like how you can change add more of your x, more of your x1, x2, and all those. Okay, so using this, we'll see how our whole, this is basically for understanding. Okay, this is basically for understanding. This is a classification problem. Here we will try to classify a few things. For example, the orange and the blue ones, right? We are trying to classify, okay, orange and blue separately. Okay, and there are like few things that you can see. If you go here, these 2 things are blue, these 2 things are oranges. Okay, and here it's totally, it's very linearly separable. You just put a line here, it should be enough, right? Even a SVM machine learning algorithm should do fine. Okay, here, can you put a line here and differentiate the orange and the blue ones? You cannot put a couple of lines and do it, right? Similarly, here, how do you differentiate this? No, your task is to put lines. See, every layer, you need to understand one thing. Every layer, right, in neural network, okay, acts as a linear component, right? Only by the introduction of activations, we are taking that linear to the non-linearity case. Okay, now we need to classify these 2. Okay, one way to assume it, okay, if you are from a statistical or mathematical background, you can think of it like this. Okay, see, what we are looking at is 2D. Okay, now I assume the plot is 3D. Okay, then I have actually displaced the blue from the orange, right? Think of it like water bottle. Okay, now the blue ones are the top of the water bottle and the orange ones are the bottom of the water bottle. If it is 2D, you cannot put a line and separate. Can I put a line and separate this blue and orange? No means, right? But now we are adding more dimension to it. So it becomes 3D. What happens when it becomes 3D? You can clearly separate it, right? When you turn your water bottle horizontally, you can cut it in center and then say, this will give you the top part, this will give you the bottom part, right? So all those things you can experiment. Actually, you can literally see how it works. Okay, for example, let's start with this. Okay, it's got x1, x2, 2 parameters, and there is 4 neurons. Okay, as the input neuron. Okay, and then there is this output neurons. Okay, using this, we have it. Okay, let's train it a little bit. Let's do some small changes. Let's do some small before even changing it. Let's run it. Let's see what it does. See, this is how convergence happens. And you see, it was able to separate with just one layer of hidden neurons. It was able to separate the blue ones from the orange ones. Okay, I leave this. Okay, now I go to this. Okay, same number of inputs, same number of neurons in the hidden layer and same number of neurons in the output layer. Okay, now let's see what happens with this. Again, it's trying to converge, it's trying to converge, it's trying to converge. Yes, you are able to achieve in this also. It's good. It's showing a reasonable performance. And you can see what is the activations it's used, what is the learning rate it's used. Well, there is no regularization whatsoever. Okay, and let's take this. Somewhat little bit interesting. I'll tell you why. Okay, now I run through this. It will try to converge this. Okay, number of epochs. You can see the epochs is keep on increasing, but we don't see much change in terms of the data. That's convergence of the data. Okay, convergence of the basically the model. Okay, it will slowly try and come up. See, but you can see the number of epochs getting increase. But that too for a simpler problem like this. Okay, imagine a real world scenario where the data is much more complex. You cannot put it algorithmically in a nice little geometrical format. Okay, so it keeps going, right? I'm going to stop it. Let's see how changing particular things. Okay, how change. I'm going to solve it very, very easily. I'll say I'm going to put another hidden layer. Okay, add a couple more neurons. Okay, let's see how fast it converges now. See, these are all the few ways that you can solve things in using changes in all those are hyper. See, whatever you see here is hyperparameter. Okay, adding a layer is an hyperparameter. Adding changing the activation is an hyperparameter. Adding regularization is an hyperparameter. Okay. So yeah, everything matters here. You can I can even add an N1 regularization, see what changes does it bring in. Not just that, if you put here, you will see the output of that neuron. What happened to my output? Okay, when it's here, when it's here, when it's here, and in the whole thing, if you see, okay, all this, right, these two, and majorly, these weightages, okay, are very important. If you see, these two are responsible for my more weight to the orange part. Okay, this is responsible for my orange part. Here it takes more blue. Okay, and you can see how the slowly it's getting converged. Okay, and by having the optimal set of neurons, by having the optimal parameters, we can actually we can see how fast it can converge. I'm going to stop this, and I'm going to add few more things so that it converges very fast. Okay, it's not just about the convergence part, it's also about the accuracy part. Okay, let's try and add a small parameter. Okay, I'm doing nothing. I'm taking this is like an augmentation. Think of this as a data augmentation. Okay, and we know it's in circular format, so we can either go with sine also, which is a really good one, because what does the sine and the cos do? It'll help you go in waves, right? So all those small things will bring in a lot of improvements to the convergence. So now I have taken one more input. See, I have not changed the input. The input is same, but I have added a transformed input. This is what we do in terms of annotation, right? You'll not take the same set of inputs. You'll annotate the input. Why annotation of the input is important? Okay, and let's see what happens by adding this annotation. You should be able to see that there is the convergence should be a bit faster than it was last time. Okay, and better accuracy in terms of literally identifying that the data is with circle, and it will also, you see that wavy pattern that arrived here. How did you get this wave? That's because of adding this sign. So one should also know what is the distribution of the data. Here the data is distributed in a circular form, in a non-linear circular form. So we thought, okay, adding a transformation that is like a wavy form will help it to take that circle. You see how slowly you, for the past two things you didn't get it, but now with all those sign, it was performing better, but not the best. Okay, so we'll see how it can be transformed also. Okay, let's say I'm going to stop this. We'll add a few things. Okay, we'll add a small regularization. Okay, with the same sign. Let's see, this particular playground, right, will help you understand what is the significance of a hidden layer. What is the significance of when I increase a neuron in the hidden layer, when I decrease the neuron in the hidden layer, what is the significance of this data transformation? Okay, so and you can see, and you can also see how the input is. Okay, x1 is like this, x2 is like this, and sign is like this. Okay, when all this combined and all this weightage, see, depends, this weights, right? This actually tells you how much weight is given. Okay, slowly you can see that, the blue part. You see the blue part is slowly coming up. Slowly, see, the reason I'm taking it very, very slowly is that it's easy. If I add couple more layers and then get it done. Okay, we can, as simple as this, we can do it. Okay, what is the difference that I did now is like I added one more layer. Okay, and in present day, this is again, this is not the full data set. This is the simplest of the form that you can have a data. Okay, where the real world data is much more worse. Okay, we'll see how it converges now. So this is the TensorFlow playground is for you to understand. I'll also add one more, and adding more layers also will make it converge much more faster. Okay, but again, the time spent to traverse and the number of parameters will increase. Okay, that is a problem. This is the final thing. This should do the trick. You can see how it oscillates. When you see it's oscillating, that means okay, it's there. It has attained a maximum amount of convergence, and further convergence is not possible. Okay, if you see except this part. Okay, most of the blue ones are kind of classified now and differentiated from the orange ones. You see the orange ones except this orange one and little bit here, which will fade off in time as we move the epochs. You see. And if it goes more for more epochs, okay, what will happen is it will try to overfit and then it will become underfit, right? That's what has happened now. So you can understand things clearly like this. Okay, we can add more also, and we can increase the batch size, decrease the batch size. See, if you have dealt with little bit of neural network, you could have come across all this. And you can change the activations. You can change it to ReLU. ReLU is a good one to have the non-linearity. Okay, so this is one tool, and another tool is what if. Okay, see, what if is another interesting tool. So you just need to go here, get started with what if. So let's say we do this classification, compare income classification on UCI census data. and they have all these things as notebooks, text toxicity classifiers. Okay, and you can also see these on TensorBoard. Okay, TensorBoard is again is something that you can use for understanding what is happening inside the network.
Dinesh, 5 minutes more, Dinesh, please.
Yeah, okay. I'm closing it off. With this notebook, we'll close. Okay, so first I'm connecting my collab. Okay, it's still connecting. Okay, initializing. It's connected. Okay, so we need to like go through each and every step. So first we are installing. Then we define the helper functions. Then we train the data set. See, for this, what does like they have it's been provided by Google itself. This what if is together with the OpenAI and Google Colab team as came together to do this. Okay, there are like you can get into these things and then see how the column gets to predicted and how the examples. Okay, one thing I'll run this through fast, Sridhar.
Yeah, please, no problem.
Okay, because this will help them to take a look at it. So reading the training data, because I want to show you the actual output. Okay, this is the training data, and as you do like df.describe, you give this, you'll get this. Okay, then we are specifying the input columns to predict. One second, let me run this again. Okay, so it has successfully run. Okay, and that is done. Let's create a train the linear classifier. Because all those are regular steps that we do. What is important is how do you invoke it, the what if tools, and we'll see the exploration ideas. Okay, it's fine. So it's taking a bit time. One second. See what we have done here is, okay, we have created and trained a linear classifier. Okay, and then we have now created and trained a DNN classifier. Okay, so once the DNN classifier also gets trained, okay, it's done. Okay, now let's see this. Okay, invoke what if tool for test data and the train models. Okay, it's getting trained on salary is greater than 50K or less than 50K. That's what the parameters we are trying to get here. Okay. Okay. See here, we can select the data points and then, okay, check for the feature values. So we can know scatter rate, scatter y-axis, x-axis, inference score 1. We can see for a particular age and how this data is distributed. Okay, so you can also see that we can plot between the label 1, label 2. Okay, see for example over 50K, under 50K. Okay, based upon age. Okay, or capital loss. You can see how we can literally change a particular parameter, and then we can pick a particular data point and then see all the data points for that particular thing, and then based on the data point you know what played a major role and which didn't play a major role. You can see that the colors by inference label 1, these are all over 50K, these are all under 50K. Okay, so the idea is to know we have taken 2 models. Okay, based on the 2 models, the what if tool uses this data and then gives you an interface like this. You can also create a similarity feature, okay, by color. See, you see all these features like the blue ones and the data points, okay, carry a similar feature. That's the idea. You can see that, the counterfactual values, what is it? Okay, and what are all the similar things that you can. Okay, so we can find the nearest counterfactuals and also create a similarity feature. That's the idea. So what really helps here is, okay, you can see the performance and the fairness also. There are like 3 things. One is the data point editor, that is the first one. And second is performance and fairness. Third is the features block. Okay, here you get to see most of the features and their representation. How many of these features? See, it's like, you bringing in the statistics inside with the comparison so that you get a overall view of telling whether this particular feature has played a major role in terms of determining this thing. Okay, and you can also see the ground truth. Okay, because just by changing the white and the black, it should not change the performance values. Okay, that's another one. The fairness, right? It should be fair enough to decide the ground truth feature. Like we can choose some ground truth. We can say age, education, country, capital loss. Okay, let's choose country. Okay, and what you get to see here is the precision and the recall based on the country and the data points and everything. So that's the another tool. What I would suggest is like it's about this what if tool and this particular TensorFlow based playground is for you to experiment and see. See, here you cannot give your data and check, but whereas here in what if tool, we can actually change the data set and run through all the steps that they have mentioned. Okay, by that way you will also be able to understand the internals of your data and your output. So with that, I think yes, we have come to the end of the presentation. I have few reference links. I'll share it. I'll basically put it in the chat or share it in the email. You can post it in the email thread, Sridhar sir.
Yeah, you can share your email ID in the chat box for further.
Okay, I'll do that. I'll do that. Okay, that's my email address. If you are interested in any of this, shoot me an email, or if you want any answers, please do. Yeah.
So, shall we wind up, Dinesh?
Yeah, sure.
So,
thank you all. Thank you very much for this opportunity.
So we thank Dinesh for being with us for the last 1.5 hours, more than that, being with us and being taken into the area of AI, explainable AI and model deployment, where I think participants would have got benefited out of it. At least they should have got some clues of what is what. And in case you can have a touch with him, so that for further or further lecture series of your extreme in your colleges or in your places and other things over there. Apart from that, Dinesh is working with. We came across Dinesh through Raja, one of our close friends. So we thank Raja at this moment also, and similarly we thank Dinesh for contributing to us, and he has been with us for the last 4 years. And Decrew Technology is one of the company which is along with us in data science, in MSc data science, which we are conducting it here. So we thank Dinesh for being with us. Thank you, Dinesh.
Thank you, sir. Yep.
So thank you, participants. We will meet you by 2 o'clock, because the reason it is